Good morning, you guys. We're going to be looking at our next unit, Unit 3, which is exponential functions and logarithmic functions. So we are starting with exponential functions. This is a topic you covered in Math 1 and a little bit in Math 2. So if you don't remember everything right away, that's okay. I'll review as I go. But this is technically a review topic. All right, in terms of this the basic stuff I'm going to cover in this PowerPoint. Okay, so if we go to the next slide, which my computer does not want to agree with. All right, there we go. All right, so we've got here exponential functions. So just remember an exponential function with base b is defined by y equals b to the x, okay? Where b is greater than 0, b does not equal 1, and b is constant. Okay. The independent variable is x with the domain of real numbers. It says, let's consider the graph at the right. Okay. So if you look at the picture, that is a basic shape of an exponential function that is increasing. Okay. There is a decreasing one, but this shape of this curve. Okay, that's what you're looking for when someone asks, is this an exponential function? Okay, knowing that you can flip it over, flip it upside down, all that good stuff. All right, the values, the y values are very, very small to the left. So in this particular picture, your y values over here are very, very small. And if you look at the table, okay, you can see your y values when you're here at 1, then you're at 1/2, then you're at 1/4, then you'd be at 1/8, then at 1/16. They're getting really, really small. But the y values grow very quickly when I go to the right. So if you're at 0 and you go to 3, okay, from 0 to 3, you go from your y value being 1 to 8, okay? And then your next y value would be 16, then 32, then 64. We're climbing off the graph, okay, very, very quickly, okay? So that's what gives us an exponential function. All right, so some characteristics, okay? Now, when I go through these characteristics here, this is mainly applying to the parent function, okay? Or that initial basic function. Once I start transforming the equations and moving them around, okay, these ideas start to change and adjust accordingly. All right, so characteristics of an exponential function, okay? The graph crosses the y-axis at 0, 1, okay? So yeah, you can see all three of these graphs, okay? They cross at 0, 1, okay? When b is greater than 1, the graph increases, okay? So that's this green graph or this blue graph, okay? So your b value, okay, so notice here, the red graph, it was 1/2, but here in the green graph, it was 8, and in the blue graph, it was 2. So when your b value, the base, is greater than 1, okay, your graph will increase. When b is between, okay, so that's indicating that it's between 0 and 1, the graph will decrease. So there's that red graph. Okay, so notice my b value is 1/2, my graph is going down and decreasing. Okay, the domain is all real numbers. I can plug in positive and negative numbers in for exponents. Okay, there's no limitations on what I'm allowed to plug in. The range, okay, is all positive real numbers, never 0. Okay, so that leads us into that next sentence. So let me read that and I'll kind of put these two ideas at the bottom together. It says the graph is asymptotic to the x-axis. It gets very close to the x-axis, but does not touch it or cross it. Okay, so that's why that range is positive real numbers, but never 0. Okay, and it's because if you look at the red graph and the green graph and the blue graph, okay, it actually looks like in this graph that they touch the x-axis. No, they get really, really close. And if I go back to this table, okay, these fractions are just going to get smaller and smaller and smaller and smaller. Well, eventually what happens is that if I'm graphing by hand, okay, I can only graph so close to the x-axis that it's just going to look like I'm touching the x-axis. But if I had some supercomputer that allowed me to zoom in, okay, that blue graph would in fact never touch the x-axis. Okay, and so that's what it means by being asymptotic. Okay, it's an asymptote. Okay. All right. So now let's just look. Now I know, don't let this overwhelm you. These are just showing you how we can flip over and apply transformations to this parent function. All right. And so that's simply what it says. Transformations can move the functions by sliding them, reflecting them, stretching them, and shrinking them. Okay. So if you look here at the first one, it's taking, okay, y equals 2 to the x. So that's that blue graph. Okay, and applying things to it. That moves it, okay? It shrinks it in this case, okay? But it looks like it's moving it, okay? But it doesn't actually move it, it shrinks it, okay? It shrinks the graph, okay? And if you look here at the second one, it flips it over, okay? And you look here, you have 2 to the x, then you have a negative 0.1 in front of it, you have a negative in front of it, and that's what flips it over, okay? All right. And then now this is where, okay, on this third one, you translate it. That's when you start moving it around. Okay, so if you start with y equals 2 to the x, and if you say 2 to the x minus 4, well, that moved it to the right. And if you say 2 to the x plus 5, well, that'll move it to the left. Then the plus 4 will move it up. Okay, so that's all that's showing you is that you're different, okay, how they change. The stretch and the compression one, okay, you won't see that a lot in people talking about that one because it really looks like you've just moved it to the left and to the right. Okay. So I can tell you in my experience, this is not something I see a lot of. I see more of questions asking about reflections and translations. But just know that you can compress it or shrink it, okay, in terms of this stretch. All right, the end behavior. Okay, the end behavior depends on whether you're dealing with the parent function or with a transformation. So there's not much I can tell you in terms of consistency. I can tell you what the end behavior is of a parent function, a simple y equals b to the x. Okay, but other than that, you have to look at the individual graphs. And we've gotten some practice on looking at in behavior. Okay, so it just says if b is greater than 1, so that increasing function. So if I go back here, okay, I'm looking at this green one. Okay, that's an increasing function. Okay, the end behavior as x goes to infinity, your y value goes to infinity. As x goes to negative infinity, f of x goes to 0 because remember, it's going to get really, 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 really close to the x-axis, which means those y values are getting really, really small and they're getting really, really close to 0. Okay? All right. And then if I have a decreasing function, so if I come back here, this red one, okay, that's a decreasing function. Okay, as x goes to infinity, y values go to 0 because you're going the other direction. And as x goes to negative infinity, your y values shoot off to infinity. Okay, and like I said here, the end behavior of a transformation will have to be considered on a case-by-case basis. So you have to see the picture to make a determination. Okay, so now let's just talk about some various forms of exponential equations. Okay. This is probably your most basic. Y equals A times B to the exponent of x, okay? That's what makes it an exponential function because x is in the exponent. Okay, you might remember these next two, but there's lots of different forms to that equation. You might have seen it with a p in there. You might see it as interest. Use that r value. That's pretty consistent. But just know that there's lots of different ways to present this formula, but it's all saying the same thing. 1 plus r is your growth rate, okay, because that's what makes it grow. That's what makes it an increasing exponential function. And your a is your initial amount, okay? Then your corresponding 1 minus r, that's your decay rate, and a is your initial amount. And like I said down here at the bottom, there are similar forms that simply use different variables, but the form, okay, the actual formula, okay, and the form of that formula is the same. Okay, you have that starting value, then you have some type of rate, a growth or decay rate, and then you have an exponent. Like I've used equations where that x is actually a t. Okay, so, and it's not meant to confuse you. It's just because after years and years and years of mathematical studies, some people have rewritten that formula with variables that are more consistent with word problems. Okay, all right, so let's go back, and when we come back in our next video, we're going to look at some sample problems of just graphing them and trying to take all this information and put it together. Okay.